Okay, here we are on the next topic. I briefly mentioned this one in the previous video about EMF. This one is called potential difference. It is also measured in volts, but it applies to literally any circuit component that uses energy. It's going to have a potential difference. So the potential difference refers to the drop in voltage across the device. And we'll talk about that a little bit more on the next couple of slides. So zoom in here, potential difference. There's a huge potential difference as you run through these wires. So the wire here compared to the ground or the tower that it's attached to, the potential difference is enormous. So the volts of this wire are huge. More common potential difference would be like the filament inside this little light bulbs here. And then also right here, this would be a case of a very large potential difference that's causing arcing of the electricity through the air, or as you might call lightning or sparks or something like that. All right, so let's talk about it in more detail. All right, as we already said, nearly every circuit component has a measurable potential difference when there is current flowing. I've just got several circuit components here to illustrate that fact. Basically, if a component uses energy, it has a potential difference. So what do we have here? These are resistors. As they actually look, if they were attached to a circuit board, those are several different examples of resistors. Here we have capacitors that could be attached into a circuit, a whole bunch of different kinds of capacitors. And lastly, just a circuit board with all kinds of things attached to it. So all of these components would have some potential difference across them. Okay, as we mentioned, potential difference is measured in volts, much like EMF. But EMF is the volts measured across your power source. All right, when I say across, I mean from the plus side to the minus side of the device. All right, so you can almost picture it like being a waterfall where upstream there is a higher potential than there is downstream. And then the higher the potential difference, the higher the waterfall, or the more, the bigger the difference between from one side of the component to the other side of the component. So here, that's a rather small waterfall, not very big. That would be like analogous to a small potential difference from one side of the component to the other side of the component, right? So you fall over the waterfall. There's some potential difference, but not much. You might have here a very large potential difference where one side of the component is very different in energy than the other side, and a lot of energy is used up through that component. So that would be a big voltage if this were a circuit component. You could also have several different circuit components all in a row, and that would be kind of like a cascading waterfall, sort of like this, where one component uses some of the available potential difference, and then the next one uses more of it, and the next one uses some as well, and then the next one uses some. So altogether, you get a certain potential difference from the start of the circuit to the end, but each component uses a bit. Sorry about that little noise there. Anyway, moving on. So, you could say there are equivalent units for potential difference. Energy divided by charge. So potential difference could be written as energy over charge, or joules per coulomb. So 1 volt is equal to 1 joule per coulomb of charge. Anyway, that's just something you should be aware of. Moving along. So how do you measure potential difference? Well, you have to connect a measuring device in parallel to whatever it is that you're trying to measure. So it's measured across. The vocabulary might help you here if you're familiar with your prepositions. It's measured across a component. Current is measured through the component, so you have to get the current that's actually flowing through there. So an ammeter has to be hooked in series with the circuit in order to find out what the current is. A voltmeter, or a measure of potential difference, has to be hooked in parallel. It has to be hooked in across the component. So basically you can think of like sticking a sampling probe in at the top of the waterfall and sticking a sampling probe in at the bottom of the waterfall. So here we've got the one end of the circuit component, and here we have the other end of the circuit component, and then we're measuring the difference in potential between those two. All right. So if you think of it as like gravitational potential energy, there is this is upstream component using conventional current. We are upstream on this side, so it's high gravitational potential energy. If this was a waterfall, it's not, right? So there's not actually gravitational potential energy in this circuit. It's an analogy, okay? So if you imagine this as being a waterfall, then high potential energy here, low potential energy here. If you're thinking of gravity and waterfalls. Now actually, of course, this is electrical energy, but you can still talk about potential energy. So it's sort of like there's a high electrical potential there and a low electrical potential there compared to the power source. All right. So keep in mind, this side of the power source is like the top of the waterfall, and then this side is like the bottom of the waterfall. And as the current flows through there, right, it's going to fall over the waterfall and end up at the bottom eventually. All right. In this case, there's only one component, so the single component there is going to take basically all of the potential, all of the volts. So this potential difference here should be equal to the potential difference across that power supply, allowing for a small amount of loss of current through the wires. All right. Okay. Cool. Hopefully you have a grasp now of potential difference, and from the previous video, electromotive force. So that gives us a good starting point for talking about a couple other things, and then eventually talking about actual circuits. All right? Thanks for watching, and we'll see you next time.